Yeah, thanks for having me here. This is a great pleasure to be here. So I'm going to talk about self-supervised learning for visual recognition. Um, I'm sure most of you are familiar with the initial slides, but I'm going to describe them briefly because it's important. So we know about supervised learning that we have an image here, you pass it through a model like an AlexNet here, and eventually you train the model so that it, given an image like a dog, it's going to basically have an output that everything is 0 except one of the neurons, which is corresponding to dog, like neuron number 2 here. Or if you go to another image like a chair, then probably another dimension is going to be 1. So we provide a lot of these images, like in ImageNet, we have 1 million of them, which are annotated in terms of 1,000 different categories. So then we train this model, which means we tune the parameters of this model. So that given a chair, it's going to provide a chair. Given a dog, it's going to say that's a dog. So that is all known, and that's called supervised learning. And this particular problem in computer vision, we call that classification. So, oh, by the way, please ask any questions anytime. I would prefer to be interrupted now, like when I talk about this. So just anytime you have questions, please stop me. Unfortunately, I don't see the chat box. I will ask one of the moderators to please remind me if there is a question that I can answer. So yeah, so we are all familiar with this, and there's a lot of papers that have shown actually if you train such a model like an ImageNet, which again has 1 million images and 1,000 categories, almost 1 million, then if you look at the initial layers of this model, these initial layers have learned some features which are generally good for visual recognition. So you can take this part of the model, this is like a deep model, you can take the initial parts of the model and remove the late layers which are very specific to the task of object classification. You can remove them and just use the initial layers and basically fine-tune that for a different task. The different tasks can be like object segmentation, it can be human action recognition in videos, it can be any other task, right? So people have generally shown that such a method that you train a model on another task and then transfer that into another task works well. So that is supervised learning. And actually, most of the systems that you see nowadays work, actually, most of them are already pre-trained on something like ImageNet. So it's rare for people, not rare, well, it doesn't usually happen that people basically train their model from scratch on their own data. They usually start from pre-trained model, but because that usually works well. So, but there are problems with supervised learning. So most of the deep learning relies on large scale label data like ImageNet, or even actually if you have your own application, you probably need to annotate some data. But what are the problems with that? One of them is annotation is in general costly. So probably natural images may not be that costly because you can ask anybody to basically say there is a cat here or a dog. But as soon as you go to other modalities like medical imaging, then that's very costly, right? You need to have somebody to tell, like you need somebody with domain knowledge to tell you if this person has cancer or not, for instance. Or annotation can be ambiguous, which means sometimes you're asking the person to do some annotation. Basically, it's actually very difficult to know what you should ask the person to annotate, right? So in classification, that's very straightforward. There is one image, you have to just assign it to one label. That's easy. But in many cases, it's actually very ambiguous. Even in image classification, if there are two objects in the same view, the annotator doesn't know which one should be the actual label for that. Usually we go with a dominant object, but dominance is not very well defined. So another problem is actually bias. So when you do annotation, you have to basically use a part of your data to annotate because of the cost, and either in selection of the data to annotate or selection of the people who have to do the annotation, you're going to introduce some form of bias into the system. And there is, of course, privacy issues. Like in many applications, you can't share the data with people that are going to see them visually. And of course, the last one, which is actually interesting and really important in my view, is that whenever you are categorizing images into multiple categories, you're limiting yourself in terms of what you can learn eventually. Like a visual system, the visual recognition system that you want to build should not be really limited to a bunch of categories. There are a lot of things that are not possible to categorize. So the last one is somehow related to this ambiguity. So it's actually not very well defined. In many applications, there is no well-defined categorization or classification problem. So that's why, like in fine-grained transfer learning, for instance. So these are main issues that I believe exist with supervised learning, which involves annotation. So recently, by recently, I mean the last 5 years, people have started working on self-supervised learning. So one of the very early works and very intuitive ones is this one, that you have an image, which is this guy. You can convert that image into grayscale to get this one. You can feed that grayscale image into a model and then ask the model to generate the original color image. So you're basically forcing the model for this image, you're forcing the model to predict the color of each pixel. Okay, actually in this particular case, this is actually the output of the model. But in practice, you're going to have input, which is a color image. You're going to grayscale it, and you're going to pass it through the model, and you're going to force the model to predict actually this image, okay, which is the color. So basically, what is happening is that you're holding out some observations about the image. In this case, that's the color, and you're forcing a black box or a deep model to predict that one. So these are usually called pseudo tasks. In self-supervised learning, we design such a pseudo task in a way that if you force the model to solve it, then the model is going to learn something interesting about the world. So for instance, here, when you say that you have to color this image, it has to color the grass in green maybe, or the sky in blue. And that kind of colorization is going to somehow tell the model that you have to first understand what is the sky and what is grass so that you can color it correctly, right? So that understanding of the texture, that this is grass and this is sky, that's exactly what we want in a pre-training. So we know that if we do this form of understanding, if the model can basically build this form of internal representation that understands what is grass, well, it doesn't need to understand this is grass. It doesn't need to connect it to the word of the grass. But as long as it builds an internal classifier, internal detector for grass, so that it can make it green, then eventually we can just tell, by a few images, we can just tell the model that whatever that you were so far you were just making green on the bottom, whatever you were making green, that's just grass. So connection to the word of grass, like English word, or the text of grass, the semantics, that is not happening in this self-supervised learning. Self-supervised learning is just trying to somehow group stuff together, like saying that whatever has this kind of texture, probably I'm gonna be always asked to make it green. So this is a particular paper that appeared, well, two papers at the same time appeared in ASoC 2016. And so here you see that a task itself is colorization. That itself is interesting because we have some old photos that we want to colorize them. I'm sure that you have seen some of these like Charlie Chaplin videos that are colorized now. But that is the task by itself is actually interesting. But in this particular work, we don't really care about that. So that is not our final product. Colorization, as I see it here, colorization is just a pseudo task that is going to help me learn features, and eventually I'm going to use those features for visual recognition. Any questions so far? Oh, I should hide the sharing notification. Thanks. Oh, yeah. Any questions? By sharing notifications, I believe you meant the bottom line. Yeah, I guess that's fine. Okay. So yeah, we're done with this. What happens then in practice, like in terms of evaluation, is that you have a bunch of unlabeled data, you have a model, you design a pseudo task or pretext task. In this case, that's colorization. You train the model to solve the task. And eventually you transfer that model, basically you copy the weights into another model. You change the latest layers because these latest layers are usually tuned for colorization only. You replace that, it's basically standard transfer learning. You're going to replace the latest layers with a new layer, and then you're going to have some labeled data set, which is not very large, and you're going to fine tune this model to solve the actual task that you're interested in. Usually this one is called downstream task. It can be like object detection, action recognition, or whatever. Okay, so this is the whole paradigm. You're going to do pre-training without labels, and then you're going to use some labels to train. Okay. So people have worked on that extensively since that time. Like, I guess the first paper appeared in 2016, if I'm not wrong. So in the past 5 years, people have worked hard on this. There was a lot of interest in the community, of course, because annotation is like has its own downsides. So there are some observations. That one of them is that when you move from smaller models to bigger models or deeper models, like AlexNet is a relatively small model, and then ResNet 50 times 4 is actually a much larger model, right? So when you move to larger models, what happens is that self-supervised learning is actually closer to supervised learning. It means that it's actually improving more. So in this case, the green one is a supervised learning, and the blue one is self-supervised, you see that the gap between them is actually shrinking as you increase the capacity of the model. So that's one thing. And the second one is actually, like, I'm going to call SSL throughout this call, and SSL means self-supervised learning, which is, well, some people call that unsupervised learning, but let's actually call it self-supervised, because it's not obvious if we should call it unsupervised. So let's call it self-supervised learning, SSL. And then another advantage for SSL in larger scale data sets is that it can actually benefit from larger scale data sets, because unlabeled data is almost available for free in many applications, right? Since you don't want to annotate it, you can just collect billions of images, right? Instead of just 1 million, you can collect 100 million images. So unsupervised data is abundantly available, and that's why unlabeled data, and that's why you can basically train SSL using deeper models, and also you can use much larger data sets. So it's actually a good idea to go in that direction. But one thing that's actually interesting in the community is that people usually do SSL using a single network, which means they use like ResNet 50, right? And throughout the whole process of SSL and final product and so on, all the time, they're just using the same model. So what we made an observation here. I'm going to tell you about one of our recent papers. We made an observation and said, let's actually not do that. Let's have the algorithm to be able to use an auxiliary model in the intermediate stages inspired by this graph. So what we mean by that is that we train a model, which is a teacher, like this model, basically, like ResNet 50 times 4, unsupervised model. And then suppose the final product that you want to make is ResNet 50. What you can do is you can pick this model, and then unsupervisedly, you can distill that in some form. You can compress that into another model that is smaller. Now, we're going to see that actually the accuracy is much better. So if you go from ResNet 50 to ResNet, it's slightly better. But if you go from ResNet 50 times 4 to ResNet 50, you're slightly better. But when you go to lower capacity models, you actually see huge boosts. So the gap between these two is caused. So all these curves, except the green one, are unlabeled. Okay, they're self-supervised. But the red one, which is our results, is that basically it's a model that is using an intermediate teacher model that is, even though it's trained unsupervisedly, but self-supervisedly, but it's actually trained with it has a higher capacity. So you train a higher capacity model and then distill it into smaller models. It's interesting that actually for AlexNet, we see that actually this model even outperforms the supervised learning, which means on ImageNet task itself, like 1 million images with 1,000 categories, if you train this way without using any labels, that performs better than training with labels. So keep in mind that for any of these points, there is no data outside ImageNet being used. Okay, they're all using ImageNet only. Green one is using with labels, and the other ones are using without labels. So that's interesting. Let's actually dive into that to see how it works. Any questions so far? Go back. Yes, I'm going to talk about the objective of compress now. I'm starting that. Okay, cool. So what happens here in compress? I'm going to call that compress throughout this talk. So what happens is we have a bunch of images here. We train a teacher model, which is like ResNet 50 times 4. We can train that using an off-the-shelf. Well, in general, for knowledge distillation, which is actually an old paper from 2015, what happens is you train a teacher model, and then you have a student model. Then you look at the categorization here. This is actually, suppose this is all supervised. You have the categorization here, you have the categorization here, and then you freeze the teacher. You train the student so that it minimizes the KL divergence between the teacher and the student. Okay, so you have categorical output here, you have categorical output here, like PDF. You calculate the divergence between those two PDFs. So in the optimal solution, divergence is 0, which means whatever this model is predicting, this model is predicting also. But this method cannot be used for self-supervised learning, and the reason is that in self-supervised learning, we don't have categorical outputs, right? Remember, we are just learning some embeddings, some representations. We don't really have a categorical output. So maybe another alternative would be to just use mean squared error loss. Just you have a vector here, you predict a vector for which the Euclidean distance between them is minimized. That's one way of doing that, but unfortunately in practice, that doesn't really work well. Usually deep learning algorithms are not really, it's not easy to optimize MSE loss in general. So we had an earlier paper in 2018 that we showed one way of doing this kind of distillation is to first cluster the output of embeddings here. You have a bunch of embeddings, you can cluster them using k-means algorithm. And now you can train the student to not only, instead of predicting the vector here, it can predict the category that vector belongs to. Okay, so here we are going to use cross entropy loss, which is actually, we know that deep learning works really well with it. Like this category, this problem is similar to ImageNet classification. You have a bunch of images. Instead of labeling them, you have a pseudo label that is coming from this clustering. So that works reasonably well. And recently, we actually have a better algorithm for this purpose, which is, we said, let's actually not even categorize them. This is kind of quantization, right? Let's not quantize them, but let's come up with some form of understanding of what that embedding is. So for a given query image, which is this brown one, we're going to define some anchor points, which are just random images, like 6 of them here. We're going to calculate the similarity between the brown one and each of these 6. That's going to give us some similarities. We're going to convert those similarities into some form of PDF. So this is a probability distribution that the higher number means that those two are close to each other. Like brown, the query and 1 are close. That's why that has a higher probability. 3 is also close, but maybe 6 is far away. That's why you see lower probability here. That's nothing but just calculating the cosine similarity between these two embeddings and then passing them through something like a softmax layer. So we get this PDF, and we do exactly the same thing for the student, right? For the same query and the same anchor points, you get another PDF. And then we're just minimizing KL divergence between them. So basically, instead of clustering them, we are saying, let's find the relationship between a point and its own neighborhood, given some constant anchor points, like random images. Let's calculate that distribution, and let's make sure that the student is mimicking the same distribution as the teacher. So in the optimum point, KL divergence is going to be 0. Well, we're not going to achieve that, but suppose KL divergence goes to 0, it means that the neighborhood of any query on the teacher and the student are the same. That means the embeddings are the same, or very close. Is it clear so far? No, the data sets that we inject to the student and teacher are the same. So the same query goes to the student, the same query goes to the teacher, and even the anchor points are the same. How your model is different from SWAV model, unsupervised learning? Yeah, so SWAV is actually, I'm going to talk about BYUL and MOCO. Well, we can discuss that later. SWAV is a form of clustering and BYUL together. Okay, thanks. Okay, I'm glad that some of you are familiar with self-supervised learning literature. Sorry if it's a little bit boring for those of you, but we're going to catch up soon. So this was the compressed one. And then the objective actually very simple. Then we have the probability distribution, which is the softmax on the cosine similarities, which is dot product here. Q is the query, A is an anchor point. And eventually we calculate KL divergence between probability of the teacher and probability of the student. So in practice, we need a large number of anchor points. That's why we use a memory bank for this purpose. So we basically collect a bunch of those anchor points and put them in a memory bank, like maybe 10,000, 100,000 of them. And then each time that we are doing this process, we don't only have 6 of them, we have actually 1,000. We have like 100,000 of these anchor points. Because it's a high dimensional space, and we need large number of anchor points to be able to represent the space. Otherwise, space is not going to be represented well. So yeah, we use a memory bank here, and also in the whole process, teacher is constant and is actually pre-trained using another SSL algorithm. Like in our experiments, we use MOCO, and usually this one is using ResNet 50x4. But this is actually pre-trained using an off-the-shelf SSL algorithm and is frozen. What is being trained here is just the student. So when we do the comparison, I showed you the linear evaluation. We show that actually when you go to smaller model, when you go to smaller architectures, actually you see a huge gap. So actually at AlexNet, it's even outperforming. I'm also showing 2 other evaluations. One of them is nearest neighbor, the other one is cluster alignment. In these 2 also, we see the same behavior. I'm really interested in these 2 evaluations for SSL. And the main reason is that linear evaluation, sorry, when I call linear evaluation means that we're going to use the features. We're going to just train a linear classifier on the top of the embedding that we have learned to do ImageNet classification. And this time we are using labels. For evaluation, we're using labels, but keep in mind that we are just training one linear layer, which means in order for this model to work well, the features that we have learned, the categories should be linearly separable there. Okay, so that's a linear evaluation. That is very standard. I'm interested in nearest neighbor and cluster alignment. So nearest neighbor basically means instead of training a linear classifier, just for each one of them, find the nearest neighbors on 1 million images of ImageNet and just see if that is correct or wrong. So that's actually very handy because you don't need to tune any parameters. Like linear evaluation, you have to train a linear model. But here you don't need to. It's just calculation of a bunch of distances. And cluster alignment have the same properties. And also it's interesting. What we do here is, well, it's actually inspired by another prior work from Oxford folks, Andrea Vedaldi. So, and his lab, of course. So what we do is we cluster the representations using k-means. And then we assign each of those clusters to one of the ImageNet categories. We just find the overlap between them and we assign them. And now that each cluster is assigned to one ImageNet category, then we can evaluate it. So basically we cluster the embeddings and then we cluster embedding exactly to 1,000 clusters. And in the best case, we are hoping that each of those clusters is going to be purely one category only of ImageNet. But that is not going to happen. Like if it happens, then the accuracy is 100%. But that is not going to happen. So what we do is we do bipartite matching to match, like one-to-one matching between the ImageNet categories and our clusters. And as soon as we do the matching, then each cluster is assigned to one of the categories, which may not be completely correct for that one. And then we evaluate to see how many of them are correct. Again, you see that actually in all of those cases, there's a huge gap between not doing compress and doing compress. So red is a compress and blue is a not doing compress. I'm actually showing here some results of clustering on this. So we get the embeddings that we learned in the end. These are actually using AlexNet. So ResNet 50 times 4 compressed to AlexNet. And then we do k-means on that to 1,000 categories. And then each row here is one category, one cluster. So in ideal case, we want all these images to be from the same category only. And keep in mind that for generation of this graph, we have not done any cherry picking. So we have just pressed a button to choose, to run k-means, choose random clusters, and from each cluster, choose random examples. Okay, so there is no cherry picking to basically find visually interesting results. So you see that actually even without cherry picking, each of these rows are roughly corresponding to the same category. It means like the embeddings that we have there, we have learned are actually very rich embeddings that are aligned with the categories. And in training these embeddings, there is no labeling used. So this is just a comparison that I showed, like in supervised on ImageNet top one, they're getting 56 and ours is getting 59. And these are various other SSL algorithms. The one that I started from, which was colorization, is here. You see that actually accuracy for colorization is not that great because colorization is not an easy task, right? So grass was one of the best examples that I showed, but there are a lot of cases that you have no idea what the color should be, right? So colorization is not a great one, but that was one of the starting points. I'm very intuitive why it's actually a good SSL algorithm. So you see colorization gets 31, supervised, which means using labels, get 56. And then we have various algorithms that are actually improving. Like MoCo is one of them that I'm going to talk briefly about, is 45, and then we get 59. So we also change this kind of compress to not go from like ResNet 50 to AlexNet or ResNet 18. We also change the precision. Like the teacher can be a floating point precision. And then the final model can be actually something like XNOR or binary model. You see that actually the teacher is pretty good, 70%, because that's floating point ResNet 50. If you go to student, that is XNOR and ResNet 18, you're going to get almost 51% accuracy. And what is interesting here is that if you train the same model, ResNet 18, with floating point, using another SSL algorithm like MoCo, you're actually getting worse. So 51.8 is for a ResNet 18 that is binary, and 51 is for a ResNet 18 that is floating point. And the reason that gap that is happening, it's actually interesting that this is actually better than that. And the reason that's happening is that this 51.8 is actually compressed from a bigger model. But the final product doesn't care, right? If you want to put together a product in the end and fine tune the model, then the XNOR model has a lot of advantages. You can run it on the edge and so on. Let me see if there's any questions. How is your model different from, yeah, I can answer that. Did you apply another command method? Another common metrics for the distance of, no, we just, oh, you mean like instead of KL divergence? No, we didn't. Yeah, it's actually an interesting idea to apply other metrics like Earth mover's distance or whatever. No, we didn't. So we just did KL divergence. That's a good question, actually. Well, comparing two different probabilities from teacher and student. Cool. Any other question before I move on? I don't see any other question here. Okay, cool. So, well, if you do supervised for XNOR, it's actually better than 51. Ours was unsupervised. If you use the same architecture with the same precision and do supervised, you're going to get 57%. So there is still some gap to fill here. So SSL is not better than supervised yet on binary models. So I'm going to move on to the next topic that I'm going to talk about, which is actually related to MoCo. So the title doesn't really, let me just talk about what you're going to understand what the title means. So recent SSL algorithms, something is very popular recently is that you have a query image, you augment it twice, you get two different images. And the whole pseudo task is that I'm going to pass these two images, which are the cropped version of this image, through the same model. The weights are shared. You're going to get two embeddings. And what you're going to say is that since these two are from the same image, most likely they should have very similar embeddings. So your objective function is to pull these two together. Okay, so that's one. Well, it makes sense, right? So if you have two different views of the same concept, then you want their embeddings to be close to each other. This is kind of tailored toward image classification, right? Because in image classification, no matter what part of this image you crop, you want always that to be a dog. It means that the embeddings should be close to each other. But in practice, this doesn't work well because, well, there's a trivial solution for this, that all the embeddings can be 0, right? Then they're going to be very close to each other. So what people did in practice, which is an old paper from 2014, is actually what you can do is you can pick some random images, and then you can use the same model on that. You can get this embedding for random images, like a bunch of these embeddings for random images, and then you can say that not only these two should be close to each other, but this one should be also far away from the random images, because most likely the random images are not very similar to this image. Well, there is a little chance that they're going to be very similar to this image, but since that chance is very low, in expectation, this kind of model is going to work. So then the whole idea is this: take an image, augment it twice, pull the embeddings of those two augmentations closer to each other while pushing them away from other random images. So this is called, like, there's an old paper like exemplar SVM from Alyosha Efros's lab that actually does that. That does similar stuff, but without deep learning. That was on SVM. So this exemplar-based representation learning is actually interesting. And people recently have worked a lot on that. And actually, this is kind of state-of-the-art work in SSL, self-supervised learning. So colorization, jigsaw puzzle counting, and those are that people have worked on in the past 5 years. They are really good ideas. But in terms of accuracy, these kind of models are performing much better. So there was a particular paper called MoCo that paper said, if I want to do this, I need to have large number of negatives. But similar to what we did in compress, well, we did it after them. So what happens is that we can't really have a lot of negatives in the same mini batch. Computation is expensive to have like 10,000 images or 100,000 images. So what they did is they actually used the memory bank. So they put together a memory bank. They say, I'm going to cache my recent data. Any data that I process, I'm going to put in the memory bank. And the oldest results I'm going to push out is basically first in, first out. Right? So you're going to, whatever is very old, you're going to basically push it out and you're going to add new stuff. It's like a queue. And why I color them differently, the reason is that when you have a memory bank, you want the memory bank to be valid for a long time, right? If your memory bank is very large, if your mini batch is just 100, each time you're adding 100 to your memory bank, and your memory bank is 1 million, then you need, some of the elements in your memory bank are going to be 10,000 iterations old in your optimization. And 10,000 iterations is very long. Your model has changed a lot. So then the embeddings that you use for your negatives are not valid anymore. So to resolve this issue, what they did is they have a momentum model, which means you are training the student, and then this model, Remember here, the models were all shared. But in this case, you're training this model, and these two models that are producing your negatives, they are actually a moving average of this model, which means whatever change that you make here, you multiply that change by a small number, like 0.001, and then add it to the old model. So basically, this model is a moving average of this guy. It's like a momentum update that you do on the weights. Okay, so what happens is that this model is much more robust. It doesn't really move very fast. It evolves much more slowly compared to this model. And that's why your negative set that you have in your memory bank are going to be more valid. So that's a very popular work. That's called MoCo. It's very well cited. It was published in CVBR 20. So I'm going to talk briefly. Yeah, that's MoCo. And then basically what happens is that you have a query image. This is just a visualization of a bunch of examples. You have the query image. You augment it twice. This is one augmentation, this is another augmentation. For this augmentation, you look for, you basically have, sorry, not for this augmentation. So you have two augmentations and you have a bunch of negative images. In this case, instead of having 10,000 negative images that I couldn't show here, I'm just sorting them based on their distance to this image, right? And showing only the top ones. So these are the top 8 that are very close to this one in the embedding space, okay? So what happens in MoCo is that this is one example. And you're saying that these two should be close to each other, and these two, this guy and each of these should be far from each other. That's why you have the labels here. So these are the positive label. This one is the positive label, and all these ones are negative labels, right? So there's 0 here and 1 here. It's a binary classification task. You're saying this one is positive for this guy, and all these ones are negatives. So this one has a label of 1, and everything here just has a label of 0. You see the labels here. But we know that most of these images, particularly in this visualization, I have actually sorted them based on their distances. We know that many of them can have the same, share the same category with the query. Like in many of them, you see that actually they're visually very similar, right? So those are the points in the memory bank that are very close. Remember, I said that we can probably ignore them for now, but actually in practice, they can actually hurt because you're telling the model some form of misleading signal. You're saying that even though that's like an animal or camel or whatever, there are some other animals which are very close to it, right? But you have to say that these two are close to each other and these two are far from each other, which means you should actually classify between different images that are very similar to each other. And that's very misleading signal. So let me make sure that there's no question here. No question. Yeah, please write your questions if you have. So, okay, cool. So what happens is we said, let's actually calculate the similarity between them, similarity that we calculated and compressed. When you do that, actually, you're going to get some distances here. So the value that you see here is the probability that we calculated. We basically calculate similarities, we pass it through softmax, and then that gives us a probability. Like here, there is 2% probability that these two are very close to each other, right? And this one is actually much lower, which is 0.6%, or here actually the best one probably is this one, like 4.7%. You see that both are dogs, right? So there's 4% or 5% almost similarity between them. So what we said let's actually not change this binary classification between close and far to something more soft. So what we did was actually very similar to compress. We have one image, we calculate two augmentations of that, we pass them through the models, and we calculate the similarities, very similar to compress, using some anchor points, and we get these PDFs, and then we basically do the KL divergence minimization. That's exactly similar. There are a couple of differences. The main difference is that over there, the teacher was a pre-trained frozen model. But in this case, we want to learn representations. We don't want to just compress it. So what we do is we initialize the teacher and a student from random. And similar to the MoCo idea, we keep the teacher to be a momentum update of the student. So teacher is a slowly moving version of the student. So the student in the feature space is taking a trajectory. This is always an ensemble. Somehow you can see that as an ensemble of all the old versions of the student. You average them all together, and that's going to be the teacher. Okay, so teacher is that version. And now we can again have a very large number of anchor points because teacher is more robust. It doesn't really change very fast. And then we can do exactly this idea, which is actually very similar to compress, as I said. But instead of freezing the teacher, we just started from scratch. basically saying that I'm going to train a student. I'm going to build a teacher which is ensemble of all the previous versions of a student, which is usually better than the student itself. And then I'm going to distill that into learning a better student. It's kind of iteratively, let's do that. So we call that iterative similarity distillation, ISD. This is published, well, it's going to be presented in a few months in ICCV 2021. So interestingly, this results in it is much better results compared to MoCo. And our hypothesis is that the reason is in MoCo, you do something similar, but the KL divergence that you do here, basically, one of them is just a 0-1 probability distribution. The correct one is 1 and everything is 0. But here we are relaxing that and we are saying that let's actually look at the similarities. So that's why I call this one, all negatives are not equally negative. Some negatives are more negative than the others. You see that here. In MoCo, we are assuming all of them to be equally negative, but here we are saying, no, let's look at the dissimilarities and say some of them are more negative compared to the other ones. If the similarity is very large, then we're not going to really push them apart, right? We're going to say those are the same thing. Let's just pull them closer to each other. Cool. Any questions so far? No questions. Okay. So nice. And one of the reasons that why this is actually working, which is interesting to me, is we actually did an analysis of the accuracy of the teacher and the student throughout the whole process. So if you do ISD teacher, this is the blue one, and you evaluate the student, that's the other color, that like orange, right? So the blue one is usually better than the orange one. That means this idea of distilling the blue one to the orange one is helping the orange one. Remember, this is the teacher, this is the student. We are kind of distilling the teacher into the student, right? Iteratively. So that idea makes sense here because the teacher is usually better than the student. But eventually in the late iterations, you're catching up because the learning rate is getting much smaller and the models do not evolve much. So the models are actually getting much more stationary in the later stages. And that's why you see that actually the teacher and the student catch up to each other. So we actually did this analysis for the previous models also, like MoCo and BYUL. And interestingly, we observed the same thing happens in those ones as well. So anytime that you have this momentum idea, that you average all the students to come up with a slowly moving teacher, usually, like at least in these two empirically, we see that the teacher is actually performing better than the student. Our hypothesis is that the teacher is an ensemble of many different students, like students in the previous epochs or iterations and the past iterations. Since you ensemble them, we know that usually ensembling is actually like the wisdom of crowds, right? When you do ensembling, you're actually improving your accuracy. So the teacher is usually having a better accuracy, but in these cases, it's not the case that you're distilling the teacher to the student, but in our case, actually we are. And in all of them, actually, again, when the learning rate goes to 0, well, small to 0, very small, close to 0, you see that the gap between them is actually shrinking. This is ISD, this is MoCo, this is BYUL. And BYUL is another algorithm I'm going to describe a little bit. So when we do evaluation, again, like I don't want to bore you with numbers, but again, we see that actually like in supervised, we get 76. There is MoCo, which is 67, we get 69. We also do resident 18, and we get, again, some reasonable improvements. Here also, we do evaluation on top 1 linear, nearest neighbor, and 20 nearest neighbor. Any question before I move on to the next topic? I see someone is typing, but okay. Cool. Yeah, please stop me anytime. Nice. Okay, let's go to the last topic that I'm going to talk about briefly. This is again another paper that's going to be presented in ICCV 21, which is, we call it mean shift for self-supervised learning. So I'm sure, well, one of the approaches that people did for self-supervised learning was clustering. So you have a bunch of images, you have a convolutional network, you do basically run k-means with convolutional network as your kernel, basically. So you have an image, you have a bunch of images as your metric. You have a bunch of images, you do convolutional network, and then you do clustering to assign to each image to one cluster, and then use the label of the cluster as pseudo labels, and then you do classification to basically improve the model so that it does better in clustering. So this is basically very similar to k-means. And that works. That was ECCV 2018. That works reasonably. There is actually a recent algorithm, like Suave is a version of this one that does clustering, but does clustering within the mini batch, actually, for one of you guys that asked about that. So Suave is from Facebook AI Research, and that's actually performing very well. So clustering basically means like we have a bunch of images, and we are basically saying that the close images should be pushed to be closer to each other. So that's the whole idea of clustering, and that's why it's actually working for self-supervised learning, because you're basically building tokens. Remember, I talked about the grass. You're saying whatever is close to the texture of grass, that should be all grouped together, and then later on we can call it the grass. Right? So that's why clustering works. There is also one more idea. Remember, we talked about the SMOCO. There's another paper called BYUL that basically it's very similar, except that they are removing all these negatives. They are saying that if you remove the negatives and just pull these two close to each other, that works. Well, it has to have this average, moving average. It doesn't need memory bank, of course, because it doesn't have negatives, but it still needs this moving average. So it seems like there is something that we don't really understand here very completely, that why it's this kind of stuff are working. So one obvious solution for this kind of algorithm might be to have zero embedding for all of them, and that should collapse to all zeros, but that doesn't happen. It's not very obvious why this doesn't happen. Researchers are still studying this. There's quite a few papers on that, but probably that's because of this asymmetry between these two models, and also they have a form of a prediction layer in the end that is making these to come non-symmetric. Maybe that is the reason it doesn't collapse. But if it collapses, that's the global optima of the algorithm. So it's actually one of those algorithms that the global optima probably exists, right? And it's actually loss equal to zero, which means all of them are collapsed to zero. But our optimization does not achieve that. So the fact that we can't solve the problem to the global optima is actually to our advantage. So let's not talk about it's actually an interesting direction in my view to understand why this is working. But BYUL is actually one of those algorithms that works really well. This was from DeepMind and works really well, actually. It's outperforming even MoCo. So, well, in BYUL, basically, you have two different augmentations. This is on the embedding space. You have two different augmentations of the same image, and you pull them close to each other. That's it. You don't have any negatives. So we actually said, let's come up with mean shift algorithm, which is very similar to BYUL, except that instead of pulling this one to be close to its own embedding, we pull that one to be close to nearest neighbors of this embedding too, or the average of them. It's kind of clustering again, right? So for those of you who are familiar with mean shift algorithm, which is a very old algorithm, what you do is you start from one point, you have a circle, like a neighborhood, you find all the points in the neighborhood, and then you average them and move the circle to the average of that. That means wherever you start, you're going to gradually move towards the center of center of mass of this kind of representation. Like any point that has a lot of points in it, that is going to somehow attract the circle, right? So there's a kind of clustering algorithm, and we said let's actually use that one to improve this kind of self-supervised learning, because we know clustering is helpful, and people have tried k-means clustering. But one disadvantage of k-means clustering is that it has some strong priors about like the shape of the cluster. Like when you do k-means, you use Euclidean distance. You're basically saying that the clusters should have a form of like a spherical, like a sphere is an idea. Like the cluster should have a spherical size, because whatever is in the cluster, whatever is inside the cluster, you're going to average them, and then you're going to look at Euclidean distance. It means like you have some prior shape about the cluster. And you're looking at long-range distances in clustering using k-means. But mean shift does not have these properties. In mean shift, you're just saying that I'm going to always look at the neighborhood of this particular image. So what we did, we actually said, let's use this kind of mean shift algorithm to improve BYUL or improve SSL. So in BYUL, each point is just pulling towards its own augmentation. Sorry. Here we said, let's, for this augmentation, this is a query. For its augmentation, let's not just pull these two together, but let's find the nearest neighborhood of these guys. So in this case, this is the query image. We pass it through two different augmentations again. We pass it through this one, and we get the query. And then we find another augmentation. We have the target. We look at our memory bank, and we find the nearest neighbors of the target. Well, we do that by replacement, which means we put this one inside the memory bank and then calculate nearest neighbors. So that's why this point itself is going to be always in the set of nearest neighbors. Okay. So the first element is always the element itself, because the distance is 0. And in this case, we have 3 more nearest neighbors. Okay. And then we average these nearest neighbors. and we pull the query to be close to that average. So you can imagine what's happening is something very similar to this, that at each iteration, we're going to move each point to be closer to the average of its neighbors. And from another point of view, that's actually a generalized form of BYUL, because if you set this k equal to 1, which means just use this value, which is distance equal to 0, that's exactly BYUL. So you are generalizing BYUL by using your neighbors. If you set the number of neighbors to 1, or basically the number of neighbors to 0, then you're going to get exactly BYUL. Is it clear so far? Can it be used in any classification area like distortion types? Yeah, so let me answer these before moving on. So BYUL, yes, there are some studies that say BYUL does not collapse to 0 because of batch norm, but there was a follow-up work by BYUL folks themselves, their journal version, I believe, that they show even if they remove batch norm, they get a very reasonable accuracy. It means the batch norm layer is not necessarily the cause of this not collapsing. So can we use SSL for reinforcement learning? Yes, there are some papers from actually DeepMind has a paper actually, I guess Pebble, from the same people who did BYUL, almost the same people who did BYUL. They actually have another paper almost at the same time that use an idea similar to BYUL for reinforcement learning. So SSL for reinforcement learning is also advancing recently. I'm not working on reinforcement learning very actively, but there are some SSL algorithms applying to that. Is it possible that the student model is more accurate than the teacher model? We don't see that. We don't see the student to be more accurate than the teacher, and probably the reason is that the teacher is an ensemble of many students, so it's natural for the student to be similar to the teacher. The teacher does grade the student, yeah, you grade based on the loss. Interesting. Did you apply another comment? No. Can it be used? Can it be used in any classification area like distortion types? I don't quite get the question. I would appreciate if you can elaborate that, Parisa. I didn't quite get that. Maybe due to using that now. Okay, I answered all of them, I believe. Oh, high resolution images is hard to feed to net if you want to use countdown. Downsampling cause losses. Yeah, so one of you guys is asking, high resolution images are difficult to feed into neural networks. So there are some algorithms on that particularly, and there are some applications. Well, this is actually slightly off the topic, but there are some applications like medical data, like cancer analysis on cell images, which are very large, like microscopic images, which are like gigapixel images. Those are very large. You can't feed all of them into one model. So what people do over there is that there are some algorithms that, you do windowing, you pass pieces of the image to get each one at a time to the model, and then in the end, you basically combine all of them to get the same result as you were feeding the whole image to the model. So people do that for high resolution images when they don't want to reduce the size of it. So I have 4 minutes left. Let me just jump to the end. So basically, we do this BYUL, and eventually, again, we show that actually we're getting better results. So forget about this WS. We can read the paper about that. This is a variation of that. Actually, it's getting a better accuracy compared to BYUL and MOCO and many other ones. And also for supervised one, well, when you have little amount of training data, or 1% or 10%, we are definitely outperforming supervised. But when we don't have that, we don't really outperform. Like supervised here is 76%, we get 72%. And of course, we are doing transfer learning. Remember, the goal of self-supervised learning is transfer learning, that you train on ImageNet and then transfer to multiple data sets. So we do that here, like to 9 different data sets, and we average them. Again, here we show that actually MSF is working. MSF is mean shift. It's working reasonably well compared to state of the art. So yeah, I talked about SSL for compressing representations, that you can use an intermediate architecture, which is much deeper, to improve the final results of SSL. I showed that in MOCO, we have some negatives. We keep all those negatives equally negative, but probably there's an advantage if you don't. It's beneficial not to do them equally. Like some negatives are more negative than the others, or less negative than the others. Let's actually look at the soft. And also I talked about mean shift, which is an old clustering algorithm, which is very classic. And then we showed that this kind of mean shift algorithm improves self-supervised learning because of the same clustering property that we saw. And I would like to acknowledge all my co-authors, students, and collaborators. Well, these are the guys who did the work. It was just great. Thanks a lot.